Last section, we worked with the ln with derivatives, and now this section is strictly integrals involving the ln. All right, so the property is if you have 1 over a single letter, if you're integrating a 1 over a single letter, before we couldn't do that, right? If I gave you like x to the -1, and we were supposed to integrate that using our power rule, we couldn't do that because you would get x to the 0 over 0. So now today is the day we learn how to integrate 1 over x, and that's just going to be the ln of x, because what did we learn in the last section? The derivative ln of x is 1 over x. So when you have the integral of 1 over a single letter, that's the key though. Just because you have 1 over something doesn't automatically mean it's going to be an ln. In a future section, what we'll have is we'll have 1 over like a trinomial here, and that is not going to be the ln of that trinomial. All right, we're going to have to do completing the square. We're going to have to involve inverse trig functions there, so don't even worry about that. Or if we can factor, it might involve something called partial fractions. Those are integral techniques for a later time. Right now, when we integrate 1 over a single letter, the answer is going to be the ln of that single letter. Okay, so a lot of these are going to be UDUs, simple UDUs. A lot of times in this chapter, if you have a choice between a weird looking numerator and a weird looking denominator, let your U equal that denominator, because if you could work a single letter into that denominator, the integral answer is just going to be the ln of that, and then we get the plus C. All right, so right here, I don't have 1 over a single letter, but what I can do a UDU. I can let the U equal that entire denominator. We'll do our UDU process there, so I'll take the derivative of that. We're going to get a 2. I don't have a 2 up here, so that's an extra 2. Remember, we balance the extra numbers. If we have an extra number, I can balance that with the reciprocal, with the 1/2. And then my U is equal to that bottom part. And so we're going to have a 1 over U, and then we tag on the du. Right? And so now once you get the 1 over a single letter, when you integrate that, that's going to be the ln of that single letter. And then now you can simply plug your x's back in, and then we're done. Now, a couple of things throughout this homework there, when you're checking answers in the back of the book, it's entirely possible they leave it like that. It's also entirely possible they use their pre-calc properties. Sometimes the back of the book gets a little bit too fancy unnecessarily, and they just try to like get, make it look neater than it actually is there. So like you can use your pre-calc properties. Like technically you can move this 1/2 up there, right? And you can actually rewrite that as the ln of the square root of 2x plus 3. I'm not requiring you to do that. Just if the answer looks slightly different in the back of the book, just you're smart enough to look at that answer and realize that those two things are equivalent. They're just using the pre-calc properties, all right? But you can just, for the whole chapter, you can just integrate that thing and just leave it alone like that. Also, what you might see on certain problems there is you might see absolute value bars around this thing, okay? If you see absolute value bars, you can either choose to write the absolute value bars, or you can leave it as parentheses right there. Technically, anytime I integrate 1 over a single letter, I'm allowed to put those absolute value bars in. What they're going to ensure is that on a definite integral, if I have numbers attached to this guy, they're going to ensure that what you're plugging in is actually positive, because you can't take the log of 0. You can't take the log of a negative number. There's no graph that exists there. So by us putting absolute value bars in, that's just a little technicality to ensure that when we plug in numbers for a definite integral, that we're actually using numbers in the domain, using numbers where we're actually going to get answers for. So it's not a huge deal. Just when you integrate 1 over a letter, you're allowed to put the absolute value bars in. Sometimes I'll put them in. Sometimes I'll just use the parentheses there. Either way, I'm going to count as correct on my assessment there. Once we start doing the definite integrals, the only time it's going to make a difference is if I'm on the AP test and I have to do the ln of something, I have a definite integral. And if I plug in numbers and I get a negative number, I don't say that's undefined. I just make it a positive number. And I do the ln of that positive number there. So try not to make a big deal. The biggest thing is we're practicing with the UDUs. We're letting the U equal the right stuff. We're integrating it. We're getting the ln's in that problem right there. If you want to put the absolute value bars in there, you can, but I'm not going to count off right now if we don't do that, okay? All right, so same thing right here. If you have an integral, if you got a weird looking numerator, a weird looking denominator, it might not even be that weird looking. But if you do got something crazy, you do try your normal tendencies that we learned when we first learned UDU. Let it equal the inside of the parentheses, let it equal the higher exponent, things of that nature. But if you have a weird looking numerator, weird looking denominator, you don't have any parentheses or square roots, then a lot of times in this chapter, we're going to let the U equal that entire denominator. That is the higher exponents anyways. But the whole point of that is we're trying to work in a single letter. So if I let the U equal the entire denominator, and I do the derivative of that, we're going to get a negative 3x squared, tag on the dx, and then you're getting the x squared part of that problem to match up. So there's our squiggles. We have an extra negative 1/3. No problem. That's just an extra number. We could always balance that with the reciprocal. And remember, the squiggle part is handled. That's already handled for us. We just need to substitute for the rest of it. So since our u is equal to that whole bottom, it becomes a 1 over u, and then we tag on the du. So it's really simple u du's a lot of these problems in here. And then once you get that situated, now here's your new property. When you have the integral of 1 over u, that's simply going to be the ln of u or the absolute value of u, ln of the absolute value of u, whichever one you want to do there. And then we'll plug the x's back into the problem. And then since we have a indefinite integral, you got to remember your plus. If you have the definite integral, you could just, you could stop right here after do your u du and switch your x's to u's using that initial equation, or you can just plug your x's back in and use the original numbers since those are the x's right there. All right, so that's pretty much your u du process there, to just working in the ln inside of those answers there. Now, that's why we couldn't really give you those problems in the past when we first learned integrals, because we didn't know that property, but now we can give you a lot more stuff to worry about. And in this next example, I just want to stress, do your normal stuff. Let your u equal the inside of the radical. Your du is at negative 2x. The x matches up, balance the negative 2 with the negative 1/2. A common mistake, a global error across the nation that students make a mistake on the AP test is when they see the integral of 1 over something, they automatically want to make that the ln, and that's not going to be the ln. This is the integral of 1 over something. It's not 1 over a single letter. So if you have 1 over a trinomial, 1 over a square root, 1 over a trig function, it's not going to be an ln. For it to be an ln as your answer, it has to be 1 over a single letter. That's why the u du is pretty powerful, because we're creating 1 over a single letter right there. And so, we learn different techniques. If we can't be a u du and we can't get that stuff to match up to get 1 over a single letter, we'll learn different integral techniques in a future chapter there, but we'll just focus on this thing here. You already know so much with the integrals, and we're learning something new there. So if you have the 1 over square root of u, this is what you already did in the last chapter. We know that this is simply u to the negative 1/2, and you integrate this using your easy power rule like we did before. So that's going to be u to the positive 1/2. Then you're going to divide it by 1/2, which means you're going to times it by 2. And then this negative 1/2 will carry down. Those 2's will cancel out. And now you get negative u to the 1/2, which is negative square root of u. And then you could plug your x's back into that problem. And remember, I don't care if you put the square root back in or if you leave it as negative 9 minus x squared raised to the 1/2 like that. You can use this or you can use this through the entire year. Either one is equivalent to each other there. So either one is going to be perfectly fine. But just make sure don't forget that even a couple chapters from now. If you have 1 over something, don't just make up your own stuff and say that's going to be an ln right away. It's got to be a single letter. So I just want to stress that. Since they stressed it at the AP conferences, they noticed that mistake quite a bit. So usually my students don't ever make that mistake. When we get the ln breakdown and the differential equation breakdown on my AP instructional report, usually my students are crushing this stuff here. So it's not going to be a big deal. We're going to get plenty of exposure to the differential equation problems. And a lot of times on those differential equation problems on the AP test, they like to involve the ln's, stuff that we're practicing in this section with the e's and the ln's. All right, e's will be another section. All right, another thing that we want to remember in this section is this property right here. Okay, if you see an ln inside that integral, automatically gotta let the u equal that ln part of the problem. Okay, so the point is, like, if you integrate cosine, you know how we can go straight to that answer. We could say that sine of x. So we have a property that takes us straight to that answer. The derivative of sine is going to be cosine. I can go straight to the answer on that. We will never learn a property like that, where when I integrate the ln, I can go straight to some answer over here and tag on the plus c. Now, we will certainly learn how to integrate this. It's something called integration by parts that we'll learn in a future section there, but you can't integrate it directly. You can't go straight to the answer. So since we're never going to have a property that allows us to go straight to the answer, we always have to let the u equal the ln part of the problem. So, and I need to avoid the problems from a future chapter. So that means when you see the ln's inside those integrals, they have to work out with u du's, and I got to make them work out accordingly, okay? And then once we get to a future chapter, I'll show you the new technique, and then they won't have to all be u du's right there. But just trust that, we're going to get you everything in due time, right? So These are easy though, all right? Because the instant you see, there is no thought process. There is no, what do I do on this problem? Instantly, when I see that ln inside the integral, I have to let the u equal that ln part. And no, it's still the inside of the parentheses. I don't want to really raise it to the whole third power. Just let it equal that ln of x part, and then do your u du process there. So just from the last section, when I do the derivative ln of something, we go 1 over that thing, times it by the derivative of that thing. So the derivative ln of x is 1 over x. Tag on the dx, and then look at our squiggles right here. I have a 1 over x dx, and then right here, since that x is on the bottom, that's like my 1 over x dx. So that's like the squiggles part of the problem. There's no extra number, so nothing to balance, and then my u is equal to the inside of that parenthesis. So instead of having the ln of x cubed, then I just have u cubed du, and that's why we just let it equal the inside the parentheses, just the ln part, because if I know how to integrate u cubed, that's just an easy integral there. So we use our easy power rule, we'll integrate that, get u to the 4th over 4, and then I can plug my x's back into the problem. And I don't care whether you write your answer like that. Sometimes people get confused. Can they write their answer like that, or can they write their answer like this? Like both of those are the same thing. It's just that ln of x divided by 4 times it by 1/4 right there. And remember, if we took the derivative of this, simplified it, we would get that guy right there, right? I would have to do a power rule there and just kind of simplify that real quick. That'll be pretty easy to do. So when you see an ln inside your integral, let your u equal that ln part. That'll be pretty good. Now, if you have an ln inside that whole denominator, sometimes I might have like 3 minus the ln. Well, I'll still let it equal 3 minus ln part, let it equal that whole denominator there. If you ever have something like that and you're not letting u equal the ln part of the problem there, I can't give you, you get like 0 points automatically, no partial credit. All right, there's one final thing, actually 2 things that we need to talk about still in this section, is this guy right here. Notice on this one, the numerator has a higher degree than the denominator. So the property I want to make sure you get down, because this will not go away. This will be pretty much sporadically in every chapter. It's not going to be there every day, but it's going to pop up quite frequently whenever, and you got to recognize it, whenever your numerator, whenever the degree of your numerator is greater than or equal to the degree of the denominator, long division is what we need to do on that problem right there. Now, sometimes if I have a linear factor, I can get away with doing synthetic division, but long division is the method that always works there. So that's what I'm going to review with you right now. Even if it's an x cubed over an x cubed and they're equal to each other, long division, all right? If you don't do that, especially in the future, if you don't do that, if we don't do that here, I can't integrate this thing, right? But once I do the long division, I'm going to turn into something that very easily can be integrated. In a future chapter, if you don't do the long division first, if you're supposed to have like 4 terms for your answer, you might only end up with like 2 terms for your answer, and you're going to cut like half of your solution away, and that's not good. So whenever you recognize this, you got to do long division. So I'm going to review that long division with you one time here, and then if you need help with that through the rest of the year, it's just going to be individual questions there. But this is just your algebra stuff and your pre-calc stuff. Remember, when you do long division, I put that 0x squared in there so I can just decrease it each time by 1 if there's no x squared term. But you look at the first thing in those, all right? So x times what gives me x cubed? That's going to be an x squared. We then take the x squared, times it by that whole x plus 5. So I distribute it through there. That's going to give us an x cubed plus 5x squared. And then what we always do there is we switch our signs. So I'm going to make that a minus, make that a minus. Those cancel out. And I get a negative 5x squared. And then I can carry everything else down. You are not done with your long division until this degree right here is smaller than this degree right here. So this is x squared, that's x to the first. I got to keep going. So you just repeat that process until that happens there. So you look at the first thing in both of them. You're thinking x times what gives you that negative 5x squared. That's going to be a negative 5x. You then take the negative 5x, distribute it through the x plus 5. So that will give us a negative 5x squared minus a 25x. And then we are going to switch the signs. This will give me a positive 19x, bring down the minus 20. And I'm not done with this because this degree right here is not smaller than that degree right here. So we need to do one more time. Look at the first thing in both of them. So x times what gives me a 19x? That's going to be a positive 19. I then take that 19 times it by the x plus 5. So that's going to be 19x. that's going to be plus 95. And then we can go ahead and switch our signs, make this a minus. So those will cancel out here, and this will give me a negative 115. All right, and remember how we had you write those answers in pre-cal last year? Once you did your division part, you said, okay, this thing was equal to this, and then you did always your remainder over this divisor. That's how we had you write those answers right there, all right? So what you're gonna do is rewrite this thing. You got your quotient part as your answer, and then we have the remainder over that divisor. And by you rewriting this problem, you have 4 separate integrals, but they're all ridiculously easy, okay? So when I integrate x squared, that's simply gonna be x cubed over 3. When I integrate 5x to the first, we're gonna go 5x squared over 2. When you integrate a number, it's just that number times x. So I got those 3 done immediately. And then when you do the integral of this is just like this very first example right here, okay? If I don't have 1 over a single letter, we're gonna need to do the u-du process right there. So technically this is like minus 115 times the integral of 1 over x plus 5. So I'm gonna let the u equal the entire denominator. This time the du is just equal to 1. So there's nothing to balance right there. So I just have that 1 over 15 in front. And then my u is equal to that 1 over x plus 5. And so that means I'm gonna have a 1 over u tag on the du. And then when I integrate 1 over u, we get the ln of u. And then I can simply plug my x's back into the problem. And then you got your plus c, and then we're done. And so there's really a few important things in this section. It's really, I think, 4 important things. One is just like these first couple examples, there's gonna be so many different looking kinds of problems where if you just do a simple u du, work in your 1 over u, you're gonna have that ln part and you're gonna be working in with that property right there, okay? And then just watch out if you don't have a single letter, then just do your normal integral there. So that's one big thing that we're gonna do a lot of in this section. The second big thing is just, if you see the ln inside the integral, let your u equal the ln. But to me, that's just more u to u process right there. But you have an approach. When you see that, do this, right? And then the third thing is this long division stuff there. This doesn't happen all that often, but we do need to practice that. Also, we're gonna do so many of these ln problems. Some of you might be already maybe think, oh, I could kind of do this one in my head there. Let's hold off on that, right? I need us to practice a lot of these first, get a lot of experience under our belt, and then a few chapters from now, I'm gonna show you a few things. I'm gonna say, hey, if you wanna do this in your head, go ahead and do this in your head. But for now, let's do our u-du approach. Let's show how we're getting that 1 over a single letter, and let's make sure we're developing good habits right there, because for years I've been teaching it that way, and then when the time is right, I'll loosen the reins a little bit and I'll show you, hey, we can do certain things in our head, but I need us to practice the right way. So, we're strong against the rest of that nation. We're not making the same mistakes that some of the other people are, all right? So just kind of just do the work that I'm having you do there. We'd be pretty good there. And then the fourth big thing that is pretty big, I saved this for the end right here, trigonometric integrals, right? So we're gonna pause the video and you're gonna jot those down. We need to have these memorized. So you already have the first 2 down, okay? The integral of sine is negative cosine, derivative cosine is a positive sign, because derivative sine is cosine, derivative cosine is a negative sign. So if that negative isn't there, you gotta stick that negative right there. You already have the first 2 down from the last chapter, but today's the day. This is a pretty important thing there. We're learning how to integrate a lot more things for you. You got the ln's under your belt, you got the long division under your belt, the 1 over a single letter stuff under your belt, and now a real important section, right? We got a lot of loaded stuff in here. The 4 remaining trig functions are in here, okay? So we have to have these straight memorized. I want to integrate tangent, you gotta have known that's negative ln of cosine. The integral of cotangent is ln of sine. So just, we want to have these flat out memorized, okay? I will prove one. I'm not going to prove all of them for you, but just right down here, if I wanted to prove to you why the integral of tangent is negative ln of cosine, you can rewrite tangent as sine over cosine. I also can do a u du on this one. We said if you got a weird looking numerator, weird looking denominator, let your u equal that denominator. So if I do a u du, if I let the u equal the denominator, the derivative cosine is a negative sign. So that matches up. I balance the negative with the negative, and so the squiggles part is matched up. My u is equal to that cosine, so that's a 1 over u. When we integrate 1 over u, you get the ln of u, and then when you plug your x's back in, you get that negative ln of cosine right there. You could do a very similar proof to prove this, you know, if you ever did kind of forget that. But typically between these two, I sometimes forget which one is on the inside, which one has a negative. And so what I do, I just kind of close my eyes for a second. I imagine that the tangent is sine over cosine, and I let the u equal that bottom part. And I know the derivative of cosine is a negative sign. So if I let the u equal that bottom part, I know that's the inside right away. And if I know the derivative of cosine is a negative sign, I know that's where the negative is coming from right away. So you could prove on your own if you wanted to, write down cosine over sine, do a u du, and get that one right there. The proofs for these guys are a little bit more involved. If anyone's interested in that, you just kind of ask me about that. But yeah, I would just kind of have those memorized. What helps me remember these last two is simply if you know your trig derivatives, you're going to know these guys right here. So I'm talking about your trig derivatives from a long time ago, all right? So we know the derivative of secant is secant tangent, right? Look what happens when I integrate secant. I get the ln of secant plus tangent. So I know the derivative of secant is secant tangent. It's using those literal same exact trig functions in there. You just got to remember the ln and remember the plus. Here's what helps me remember this one. I know the derivative of cosecant is a negative cosecant cotangent, right? From our derivative, the derivative of cosecant is a negative cosecant cotangent. So when I integrate cosecant, I get my negative. The derivative of cosecant is a negative cosecant cotangent. So when I integrate the cosecant, I get negative cosecant cotangent. I just got to remember the ln and remember the plus. So that's the format of those in there right there. So just kind of memorize those. Here's the good news, all right? I know sometimes we get confused on the trig integrals, what to let the u equal, how to approach it. The good news is this takes some of the guesswork away. There is no, can I integrate this or can I not integrate this? Here's what's comforting is anytime I see the integral of any single trig function, I know I can integrate that. I know I don't have to do anything weird on that problem there. You just have to have this memorized right there, right? And then you want to have it memorized. You don't want to be proving it every single time there, especially if I give you the tangent of like a quotient or something like that, or the tangent of 5x. You just want to just know, just let u equal that 5x there. So like if I give you the integral of secant, make that ln of secant plus tangent. If I give you the integral of secant of a weird angle, same rules apply that we learned when we learned u du before. Let your u equal that weird angle. Take your derivative, balance that 1 over 80 with the reciprocal, and then once you get that single letter involved, do your integral, get the ln of secant plus tangent, and then you can plug your x's back in, right? So you don't want to have to rely on like proving this stuff every single time. You just want to have those automatically known and then go straight to it. So a lot of u du in this section, a lot of stuff loaded up. I think each thing by itself is actually quite simple, but it's just several important things all combined in this one section right there. So hopefully we gave you some thorough notes. Hopefully you got these things memorized. Hopefully you got the approach down. And what we want to study on the integrals always is what the problem looks like and what to do at the beginning. So what to let the u equal. So hopefully these notes gave you some things to try there. Let it equal the denominator. If you got the higher degree on the top, let that equal. If you got the trig stuff, a lot of times you let it equal the weird angle and stuff still. So just practice that as much as possible and then bring me some questions with that homework there.